Okay, today we're going to talk about 3.3, 3.4, and 3.5, which is survivorship curves, carrying capacity, and population growth and resource availability. By the end of this lesson, you should be able to explain survivorship curves. To accomplish this goal, we will describe the three different survivorship curves and identify the curve which explains K-selected and R-selected species. So to begin, survivorship curves are a line graph that displays the relative survival rates of a group of individuals of the same age in a population. So it shows the survival rate of birth to the maximum age reached by any one member of the population. So we use this to gauge how likely certain individuals are to survive to a certain age. So here are the three types of population of survivorship curves. So you're going to notice over here we've got the percentage of survivors and the percentage of maximum lifespan. So with our type 1 survivorship curve, we have 100% survivors at age 0, and it's pretty close to 100 at age 50. And when we get out here to about, we'll say 80-ish, we start to show a severe decline, and 0% of the population is still alive at around 100 years old. Type 2 shows a steady decline in population as time goes on. So at the beginning, there's 100%, and that's going down steadily, so that half are left by 50, and by 100, everybody's gone. So you have the same chance of dying at any point on the type 2 curve. With type 3, we see the complete opposite of type 1. So we've got 100% of our individuals here, and by a very short time in our lifespan, most of them are gone. So which of these belongs to an R-selected species? Remember, these are the species which produce a lot of young, don't provide a lot of care, and usually have really short lives, versus K-selected species, which tend to have fewer young, invest more in their care, and live long lives. So let's see. So starting with the R-selected, we see that type 3 represents our Rs because we reproduce a lot real quick and then we die off pretty early. And type 1 and type 2 go to our K-selected species because they live longer, there's more parental care, and this is important to our curves. So this shows a couple of different species. We show that as an infant, there's a lot of parental care, so most infants survive till adulthood, and then as we get older, our population starts to decline. In trees, they produce a ton of acorns. Some of them make it to saplings, and very few of them make it to adult trees. Here we show a bird. The bird has an equal chance of dying when it's an egg, when it's an adult and growing, and then when it's a full-fledged adult. So our R-selected, K-selected. So, carrying capacity. By the end of this lesson, you should be able to describe carrying capacity and describe the impact that carrying capacity has on an ecosystem. So to accomplish this goal, we're going to first describe what carrying capacity is, and then describe the impacts that carrying capacity can have on an ecosystem. So this is really closely related to population density, survivorship curves, many of the things we've been discussing. So in short, carrying capacity is the maximum size of a population that an ecosystem can sustain. So that's this line right here. There's just not enough in the ecosystem to support more than that, and there's no benefit to the population to support less than that. So we have what's called the carrying capacity, and this is where that K-selected word comes from. So K-selected species typically are at and stay below the carrying capacity, where the Rs quickly explode over that. So this population growth right here is that R. So if we go back, we have overshoot. This is what happens when a population goes above that maximum population size. So what does this mean for a population? If your carrying capacity is right here, but you overshoot up to here, what does that mean? So we know that overshoot leads to dieback. So population can't support more than the carrying capacity, so things have to die. The lack of resources from the high population can lead to die-off or conflict or disease. Regardless, it causes our population to decrease below that carrying capacity. Here's an example of the kebab deer population. In the early years, there was a huge growth rate. Their population had enough to eat, they were reproducing, but when we get to about 1917, we start to see problems. So fawns are starving, the population is still growing, and then we have a huge die-off where 60% of the herd starved over 2 winters. The population came under and now is staying just below that carrying capacity here of K. So let's look at how R and K selected species respond to the carrying capacity. So R selected species have quick population growth, and whenever there's a new habitat, their population just explodes. So this is why we say that a lot of invasive species are selected, because they can adapt really quick and they just reproduce like crazy and take over. So we see it's kind of like boom or bust. So there's a lot of resources, they go crazy, reproduce a lot, and then now there's no resources, so they fall and their population goes down. But then now there's a lot of resources, so they explode again, and it just keeps going in that cycle. On the other side, we have K-selected species. Now we know our K-selected species typically respond slower, so they have a slow population growth, and it's controlled by that carrying capacity. They don't tend to have huge overshoots and these giant swings in population. Because their population growth is so slow, they typically have delayed reproduction, and that's what we see when we look at this graph. So this leads us into resource availability. So our goal here is to explain how resource availability affects population growth. So we're going to describe what resource availability means and explain the effect of different resources on a population. So we've talked a lot about populations growing and carrying capacity, but what actually limits a population's growth? Populations are limited by environmental factors, such as the availability of resources or space. Resource availability and total resource base are limited and finite over all scales of time. So this is not just right now. It could be right now, but in the grand scheme of things, overall, there's a limited amount of resources. So this will control the overall population. So how does it affect a population? So here's a really crowded population of penguins. When resources are abundant, population growth increases. So that's kind of what we're looking at for human population right now. We see an exponential growth rate, and that goes like that, shoots right up. So when resources are abundant, population growth increases. We'll remind ourselves about those deer. What happens when resources are not abundant? When there's an unequal distribution of resources, it increases death, we call mortality, and it also decreases fecundity, which is reproduction. So that's a logistic growth curve, and it looks more like an S. We talked about predation, competition. So predation causes population growth to decline to or below carrying capacity. So we see when resources are good, our prey goes up. As the prey goes up, you'll see a little bit of a lag, and then the predator population goes up. But our preys become too high, and now they're decreasing. As a result, our predators have to decrease, and this just continues on and on. So to summarize, there are 3 types of survivorship curves which show the survival rate from birth to death of any one member. Populations that overshoot their carrying capacity suffer dramatic diebacks. When resources are abundant, a population will grow, and that's our exponential growth. And when resources are limited, a population will decline to or below carrying capacity, and that's this logistic growth. So we call these J curves and S curves.